There are many of them, but we will discuss some of them. And some of them I will skip. I've not actually mentioned the name, but I'm not going to explore. They will come too complex for you. So let us go through them one by one. Precision scaling is the most interesting technique. So I will separately discuss what is, FP32 format, what is FP16 format. But I'm sure at least you must have heard of the name floating point and fixed point and integer. So how do we, represent them? How do we compute the accuracy and range? That I will discuss separately. But just for now, you can please read it and try to just understand. So we have different number representation system. Some of them use more number of bits, for example, FP32. Some of them use less number of bits. Some of them just represent integer numbers. Some of them represent only fixed point numbers. So here, depending on how many bits they use, how many exponent bits are there, how many mantissa bits are there, they will have different range. They will have different accuracy. So as you can see now, more the accuracy, the better it is, right? But now we are talking about approximate computing. So we like to work with very little storage. Suppose instead of FP32, if we can use just FP16, it is good for us. But the cost is that we have to sacrifice the accuracy. So, and another thing is like, this was IEEE standard format. This was also IEEE standard format. But recently, researchers have proposed brain floating point. So brain floating point here, although the total number of bits is 16, but here number of exponent bits is same as that in the FP32. Although the total number of bits is 16, but they have sacrificed on mantissa. They have not sacrificed in the exponent bits. So exponent bits are same as that in the FP32. That's why its range is same as that of the FP32, because range is decided by the exponent bits, number of exponent bits. So fixed point versus floating point format. Here I'm reviewing it for the first time. Later on, I will explore it in full detail. So in fixed point system, we have a fixed number of bits reserved for integer and fractional parts, regardless of how large or small the number is. For example, suppose we have so now let us talk about decimal number system. Suppose for just for a moment you forget binary number system. We are all very familiar with decimal number system. So we have this number system where suppose we have total of 10 digits. I'm calling it digit because it is decimal number system, out of which I use 5 digits for integer part, 5 for the fraction part. So what is the largest number I can represent here is that the largest number is if all of them are 99999. So this is the number. And what is the smallest number I can represent is, of course, 0, but the number right above 0 is this one, where all the bits are 0 except this one. The last bit is 1. Right? I hope you agree. So this is the range of numbers I can represent if I use fixed point number system. In floating point, the number of bits for integer and fractional part is not reserved. Instead, it reserves certain bits for the significant and certain bits for exponent. So that's what we had here. So we had actually in a floating point, we had this many number of bits for exponent and this many number of bits for mantissa. So, okay, so this exponent and mantissa is different from integer part and fraction part. Please remember, right? Here in floating point we have exponent and mantissa, whereas in fixed point we have some bits or some digits for integer, some bits for fraction. That is not same as exponent and mantissa. Now, if you have an FP number system with suppose in base 10, we have 10 digits with 2 digits for exponent. So the largest value we can represent is this one, and smallest value that we can represent is this. So how we came up with this, I will discuss separately when I actually discuss the floating point number system. But assuming, if right now you just assume this is correct. But so one thing you can see is that this range is very small compared to this range. This range is 10 raised to power minus 49 to 10 raised to power plus 50. So this is a huge range. Here the range is much, much smaller. Okay, this range is much smaller. So that's what I was trying to explain, that how in floating point number the range is very high, but of course the precision is smaller. And in fixed point, range is small and precision is higher. So what is the benefit of fixed point? So, so the obvious limitation of fixed point is range is smaller. As I already showed here, the range is smaller compared to that in the floating point. So in fixed point, gaps between adjacent numbers is fixed. Whereas in floating point, the gaps are not uniformly spaced. You will understand this when I come to floating point and fixed point. So I will discuss about floating point in full detail. But for now, you can maybe take it. So gaps are not uniformly spaced. There are large gaps between large numbers and small gaps between small numbers. So here you can see this is the a sample of 8-bit IEEE like. Why I'm calling it IEEE like? Because in IEEE there are FP32 and FP16. This will be a very huge number system. So that's why to make it a smaller number system, we have just used 8-bit, but along the similar guidelines. So here the gaps here are very large. That means we can represent -4, we can represent -5, but we cannot represent any number between -4 and -5. Whereas here I can represent a lot of number between 0 to -2. I mean, this is log 2 of that. It's not exactly, I mean, -4, -5. It's just 10 raised to power -4, 10 raised to power -5. So one thing is that in floating point, gaps are not uniformly spaced. That's why it can have such a large range, because it uses non-uniform gaps. And fixed point hardware is generally smaller. It has less number of transistors. It has shorter wires, and it is more energy efficient than than the hardware units for floating point. Okay, fixed point hardware, it is smaller and more energy efficient than the hardware we have for floating point. Okay, so this point I will probably skip for now. I will come back to it later. So this will be a little difficult to explain now. This one let us discuss. So let us see for LXNet. In any neural network, we have different layers. Okay, we have for example, first layer, suppose convolution layer, then pooling layer, then activation layer, and so on. So this shows the range of activation values. That means whatever output is generated at by each layer, what is the range of values? So in layer 1, the values range between -691 to 662. Here in layer 2, it ranges between -228 to almost 224. So here you can see that the range of values is not very high. We use floating point when the range of numbers is very high. But because here the range of numbers is very small, we can just use fixed point. Okay, we can just use fixed point. For example, suppose we use 8-bit fixed point. Okay, just for now, you ignore the numbers after decimal. Okay, you ignore these numbers after decimal just for now. Okay, and you assume that here in this 8-bit, whatever integer. Now we have an integer because we are ignoring the fractional part completely. So if we allow both positive and negative numbers, so we can store between -128 to +127. Right, with 8 bits, -128 to +127. So we can represent these layers just using 8 bits, 8-bit representation, 8-bit fixed point. Okay, and for these we can use 9 bits, and for this we can use maybe 11 bits, 11-bit fixed point. Okay, so we don't need floating point, means we will have to use either 16-bit floating point or 32-bit floating point. We don't need that. We can just work with fixed point. Okay, so inputs of all intermediate layers are activations whose outputs are compressed through sigmoid. So this causes the dynamic range. Actually, this one will be a little difficult for you to understand now. But at least this point you can understand. What is the justification for fixed point? I will come back to it later. This lower part. Once I explain to you more about CNNs, then I will come back to it. But at least this point you can understand that if our ranges are small, we don't need floating point. We can just work with fixed point, because one of the main advantage of floating point was its very high range. But if the range is small, we can just use fixed point. So what are the optimizations which we can do based on precision scaling? So see, just a minute, can I explain this? Then you can ask.
Yes,
let me just explain this slide then. So suppose if we can use precision scaling, that means instead of 32-bit floating point, I can work with 16-bit floating point, or instead of floating point, I can work with fixed point. So this is the idea of precision scaling. That means we are able to work with lower precision. So now if we can work with, suppose instead of 32-bit, if I can work with 16-bit, then half of my data path, that means if we have suppose this is around 32. Suppose this is our 32. Actually, it's not coming out because of my style. Let me draw it again. Suppose we have 32-bit data path, where we have 32, parallel lines to transfer the data. Now, instead of 32-bit, if I'm working with 16 bits, then half of my data path is unutilized. I can power gate it. Okay, or I can pack multiple data in the same word. That means in the same word, I can pack two integer, two 16-bit data. For example, here 16-bit and here 16-bit, and I can simultaneously process it. Or if I don't want to pack two, then I can, instead of having a 32-bit multiplier, I can just work with 16-bit multiplier. And as you can expect, 16-bit multiplier will be smaller, faster, and more energy efficient. So if my data width is reduced and whatever precision loss happens, if I can tolerate it, then I can make my circuit very, very efficient. Okay, so now please ask question. Whoever had question.
Yes, sir. In previous slide, sir. Sir, yes. Layer 1, sir, what is this range for?
So okay, so actually in layer 1, suppose this is neural network, right? Suppose this is for LXNet.
Yes,
now LXNet will have suppose 5 convolution layer, 3 FC layers. Now this is the range of values which we see in that layer. Okay, this shows the value of the output of each neuron in that layer.
Sir, basically weights.
No, it's not weights. It is the weight into input.
Okay, weight.
See, we have input activation.
Output of a neuron. Neurons.
The weighted sum.
See, just you first listen. See, we have input activations. Input gets multiplied with the weight, that becomes the output activation. And output activation of one layer becomes the input activation of the next layer. So here this shows the output activations of a particular layer. Okay, that means the weights of that layer multiplied with the input to that layer, that gives you the output activation. And output activation of one layer becomes the input activation of the next layer. So this activation is also called feature map. Sometimes you will hear the word input feature map and the output feature map, which is same as activation, input activation and output activation, which is same as input feature map and output feature map. So input feature map gets multiplied with the weights and it gives you output feature map. Okay, and this lower portion I have not discussed. I will come back to it a little later. So is it clear, everyone? Okay.
Sir,
yes.
with each layer, the range keeps getting less. so like it becomes more precise. That like
Yeah, actually, so your point is correct. So here what happens is that actually we will use sigmoid, so their output values will be compressed. So this is an observation for this network. It's not necessary for all the networks, but yes, for this network, for example, here this layer will have larger range of values, but this can happen. This can happen that for a particular network, that the range of values is getting smaller. So that's one of the observations you have made, which I will show a little later. That if we can in fact have, for example, 11 bit for this layer, 10 bits for these 4 layers, and 8 bit for last 3 layers. We don't even have to use similar number of bits for all the layers. We can have less number of bits for later layers. Yes, that's one possible optimization.
so, sir, like is there a possibility ever that the last layer would have more range than previous layers?
No, that can happen. That can happen. It's not that we are. It's not that that's always the range is going to reduce. The range could increase. Yes. Even here, right? You can see like layer 4 has more range than layer.
Yes, sir.
Layer 3.
Layer 4 has more range, 145.
Yeah. So this is not always the case that always the range will reduce. Okay.
Yes.
Okay. So what is the other optimization which is possible from precision scaling? So it increases spatial and temporal locality. I will discuss how, which increases the coverage of memoization. So suppose you have suppose 9 pixels. Okay, let me repeat. 1, 2, 3, 4, 5, 6, 7, 8, 9. Like suppose some of the pixels, if you were to take this wall. Now their values may be 3, 3.1, 3.2, 2.9, 3.1, 3.05, 3.01, 3.1, 3.09. Okay. So now if you do precision scaling, suppose you just round off all of them to the nearest integer, then all of them become 3. Isn't it? If you were to just round them off to the nearest integer, then all of them become 3 only. Then all of them become 3, 3, 3. Okay. So now your scope for memoization will increase. What is memoization? I will tell. So what in memoization, we use lookup table instead of doing the actual operation. Suppose I think I have that memoization here, but let me just first explain in simple term. Suppose you have the numbers A into B equals to C. Okay. So now usually, as you know, multiplication takes a lot of cost. So what you can do, you can store this result in a table. So you have the input number, suppose 7, 8, and then you can store the answer 56. Next time, when you see one of the operand to be 7, another operand to be 8, you don't actually multiply them. You just you just take the value from here, you read it, and that will give you the answer. It is just like log tables, right? It's not that every time you have to compute the log of something, you really do the full expression and compute the log. You just read it from the log table. So that's why, multiplication is somewhat cheaper, although it is more costly than the multiplication. But there could be some operations like sine theta, cos theta, or tan h or exponential, which operations are really, really complex or time consuming. So instead of all the time computing them, you can compute them once and store their value in a table. That's called lookup table. And instead of doing those operations, you can use those values. So this increases the coverage of, that's called memoization. You are memorizing the result. Okay, you're not doing the computation, but you are getting the result from a memorized values. Okay, so now once you replace all of them with suppose 3, then your ability to read the values from lookup table will increase, because here, for example, if you have 3 versus 3.2, you cannot use this memoization table, lookup table. But once you have just done precision scaling, then you can use this table. Okay, so that's the idea. That means it increases the scope of using memoization, because those minor differences were there which were preventing use of this memoization table, they go away. So for example, here, instead of, suppose one more entry could be 3, 9 or 27. Of course, this one looks very trivial, but just for example, now here, all the numbers which were 3 point something, they all become 3. Right? All of them now become 3. So you can just use this table for all the 9 pixel values. And another thing which can happen is it turns a floating point operation into a trivial operation. For example, if suppose these numbers were 0.1, 0.2, 0.15, right? Suppose these 3 numbers were there and you round them off to the nearest integer. Then all of them become what? 0, 0, 0, 0, right? All of the 3 become 0, 0, 0. Then you don't need to do computation, because we know that when x plus y, if either x or y is 0, x minus y, x into y, if one of the operand, for example, in multiplies 0 or 1, then you don't have to compute any operation. So then the operation itself becomes trivial. Your number of operations reduce. So precision scaling reduces your number of operations to be done. So remember, there are 2 things happening here. First, we do precision scaling, and then precision scaling helps us to increase trivialization. It converts many operations into trivial operations. So Mohit, is it clear? Mohit? Mohit? Yes, Anupam, please ask question. You don't have to raise hand, actually. I will not be able to see raise hands here. You can just directly unmute yourself. Whenever I ask you for a question, you can just unmute yourself and ask question. Don't raise hands. Okay.
Right, sir. Right.
Yeah, please ask question.
Question is, with this precision scaling that we are doing, sir, isn't the error also increasing more, sir?
Yes, error will increase. Yeah. So that portion will come separately. Here we will use this technique only in an application which can tolerate error, such as neural networks. So how neural network can tolerate this error, that we will discuss later on. But what are the techniques we can use to do approximate computing? That's what we are first seeing here.
Sure. Thank you.
Okay. Yeah. So that's why the first question which will come to our mind is, how can we even do it? Because we are all trained with exact computing paradigm.
Yes, sir.
So that's why I'm saying in many applications we can tolerate this error. We don't need so much precision.
Okay.
Okay, you can lower your hand. And anyone else? So now let us go forward. So again, you don't have to remember any of these circuits. In exam, we will not ask you to draw anything unless we specifically tell you to memorize that you have to remember this figure, the last. But in general, just try to understand how it works. If you don't understand, it's fine. So in memoization, what we do, we compute, we take the operand 1, we take the operand 2, we have some, XOR just for hashing, and we read it, we read the memoization table. Here we are assuming that memoization table is already filled up. We are just reading the value from memoization table. We are not writing anything to the memoization table for now. And if we get the result from memoization table, we will read that result here. And at the same time, sometimes we don't get result from memoization table. So to save time, in parallel, we also do the actual ALU operation. So now, depending on some condition, whether we found out the data in memoization table, whether there was the exact match or not, we will either read the ALU result or the memoization table result. Okay. So this was exact memoization. In the approximate memoization, as I said, we are doing precision scaling. So we will, suppose we skip some of the bits. Okay, suppose we drop lower bits. That means all the fractional bits we will drop, so that our number is just a pure integer number. We are not even discussing any fixed point number. We are just dealing with now integers. So we have dropped some of the bits. So now we take hash of them and then we XOR them. Rest of the operation remains same. So here the only difference is instead of doing the hash of the XOR operation for all the bits of operand 1 and operand 2, here we do that after ignoring certain bits and bits drop. Okay, that's the approximate memoization. So here, as you can see, because we are ignoring the n bits, so regardless of what those n bits are, because anyway we have ignored those n bits, our results will match just based on the top bits. As long as top bits are matching, whatever was the value of lower bits doesn't matter, they will anyway match, and we'll get a hit in the memoization table. Okay, now another strategy is called loop perforation. So this is very, very simple. Here we all know, right? I'm sure you must have seen of this kind of for loop where we do I++. When we perforate the loop, instead of doing I++, we perforate by a factor of p. So we do I plus equals to p. That means we are skipping certain iterations of a for loop. Okay, we are skipping certain iterations of a for loop. So this applies to several global computational patterns such as Monte Carlo, iterative refinement, searches, test case, enumeration. Let me discuss one example of Monte Carlo. So Monte Carlo is a very useful approach. There are some students here who are from that electronic circuit background. They do the Monte Carlo simulation all the time. So let us see what it is. So Monte Carlo was probably some famous person. Okay. So here, suppose what we do, we draw a square here, and then we also draw a circle. So now you throw darts, okay, or you can generate some points, but let us use that terminology. Suppose you are free, you have all the free time, you keep on throwing darts, okay. So the area of circle divided by area of square, that will give you the ratio of, on average, that means probabilistically speaking, how many points or how many darts that you throw will fall inside the circle versus how many of the darts are total. Assuming all your darts fall within this square itself. Let's suppose you are always sure that your dart will always fall within the square, but sometime it may fall inside the circle, sometime it may fall outside the circle. Okay, so that's why the ratio that the ratio of the area of circle divided by area of square is same as the number of points which fall inside the circle divided by number of points which are total generated. If you throw large enough number of darts, or if you generate large enough number of points, and then area of square here is 1 cross 1. Suppose you take a unit dimension square, then area of square is 1 cross 1. Area of circle is how much? What is the area of circle here? Let me ask someone. Prashant Jaiswal?
Yes, sir.
What is the area of circle here? What is the
pi by 4?
Yes, pi by 4. Yeah, because the r here is 1 by 2, and the area is pi r square, right? So the area will be pi by 4. So now with this you can replace the value of pi. So if you do this experiment, you can get an estimate of pi. So whole idea is we are using Monte Carlo method for finding the value of pi. Okay, so this is the value of pi you get by pi equals to 4 into number of points inside circle divided by number of points generated. So now I have written a code for finding value of pi. Okay, so suppose we have 1 lakh. So this n iteration is the number of points which are generated. So this is 1 lakh points I generate, and these are their x and y coordinate. And how many of points fall inside the circle? I just do some random. I'm sure you know how to seed a random number. Now for I generate 1 lakh point, so I generate X and Y. Okay, and I make sure that both X and Y are less than 1. Okay, both X and Y, they are less than 1. So, and then I find out this, actually this should be drand divided by rand max. This is not double, this is just one division by rand max, just to make sure the number that I generate should be less than 1. That means it falls within the square, always. Now, whether it falls inside the circle or not, for that, it has to always meet this condition that x square plus y square should be less than 1, because that is our circle. So if this number is less than equals to 1, then this point is inside the circle. And with this pi equals to this expression, which I computed on the previous slide, we can find out what is the estimate of pi. Here is the answer I get. I have run this program. You can also run this program if you want. I will upload the source code. Actually, I have given this link also if you want to. This program is available on that link also. So here you can see with increasing value of n, my estimate is getting better. It's not always the case that it will always get better, because afterwards it's a random number generation. So depending on what is the quality of the random number generated, sometimes it may even go down. But in general, it will be true that as you increase the value of n, your estimate of pi becomes better.